From the KZN 2017 Prelim. Two blocks of different masses are attached to each other via a light, inextensible string which is placed over a massless and frictionless pulley. A block of mass 2 kg is placed on a smooth surface and attached to the wall by a second string, which makes an angle of 70 degrees to the vertical as shown in the diagram below. A second block of mass 5 kg is left to hang freely. The entire system is in equilibrium and all forms of friction can be ignored. Whenever you have forces that are in equilibrium, the net force acting on the object should be equal to 0. Okay. Now, I want us to imagine that we have a Cartesian plane for this block. We have T1, which looks like that. And then, so whenever you have an angle such as this one, you are going to resolve that into its components. You will have a vertical component and then you will also have a horizontal component. From trigonometry, we know that that is 70 degrees, that's a 90, so that's a 20 degrees. Okay. 2.1.1. State Newton's second law of motion in words. The net force acting on an object is equal to the rate of change in its momentum. 2.1.2. Draw a labeled free body diagram for the 2 kg mass. We have 4 marks. The marks there indicate the number of arrows that you must have. This is the 2 kg block. Since it is placed on a flat surface, we are going to have a normal force. And then the weight always acts downwards. To the right, we are going to have T2, and to the left, we are going to have T1. You can draw it like this, or you can do this. So we said that for T1, we can resolve this into its components. You can draw T1x, and then you're going to have a vertical T1y. So these two are exactly the same thing. 2.1.3. Determine the magnitude of the tension force T2. So we're just going to use this block because it's only 2 marks. So it means that we need to use the block with the most information. For the 5 kg block, I have the weight acting downwards and then I have T2. So some of the forces that are acting in the y component should be equal to 0 because we said the system is in equilibrium. So I'm going to have T2 minus the force of weight. So I'm choosing upwards as positive. So T2 is equal to, this is m multiplied by g, which is equal to 5 multiplied by 9.8, which is equal to 49 newtons. Excuse me. 2.1.4. Calculate the magnitude of the normal force exerted on the 2 kg. So we said that the entire system is in equilibrium. And then we know that T1 is resolved into its horizontal component, and then we also have Ty. And then to this side we have T2. When the system is in equilibrium, it means that T2 balances the tension in the horizontal component. In other words, it means that Ty of x should be equals to 49 newtons. Okay, so now in this right angle triangle, I have what? The opposite over the adjacent. So I can use tan. Then I'm just going to use 20 degrees because here I'll have a 70. So there, that must be a 20. I'm just going to use, so this will look like that. And then that's a 70, that's a 20, and this is a 90. So yeah. And then this is t of y, and that is t of x. Tan 20 degrees is equals to t of y, that's what I'm looking for. T of x, that's 49. T of y should be equals to 49 tan 20. So I am getting 17.83 newtons. And then now I'll just say the sum of the forces that are in the y component is equals to 0. So when you look at this body diagram, you can see that T of y and the normal force are going in the same direction, and then the force of weight is going in the opposite direction. So I will add the normal force. I will also add the force of tension in the y component. Then I'm going to subtract the weight. So the normal force should be equals to F of weight, that is 2 times 9.8 minus 17.83. So I'm getting 1.77 newtons. 2.2. An astronaut has a mass of M1 is equals to 94 kilograms. He goes on a space mission to the moon. On the moon, he finds that he has a weight of, so his weight is equals to 152.28 newtons. The mass of the moon is, that's going to be M2, 7.348 times 10 to the power of 22 kilograms. Calculate the gravitational acceleration on the moon. Well, that's easy. You are given the weight, and then you know that the weight, it is mass multiplied by gravitational acceleration. 152.28 should be equals to his mass multiplied by the gravitational acceleration. So this is 1.62 meters per second squared.